Hello people, this is lecture 2. Today we will discuss the fast Fourier transform, an algorithm that accelerates Fourier analysis. Like the discrete Fourier transform, the fast Fourier transform or FFT converts a signal from its original domain, which is called time domain, to a representation in the frequency domain, and vice versa. However, FFT determines Fourier analysis faster than computing it directly using the naive DFT series discussed last week. It is interesting to note that FFT is one of the top 10 algorithms with the greatest influence on the development of science and engineering in the 20th century. Last week, we discussed the DFT and IDFT series. If you remember, the first series converts a discrete signal of n samples into its n frequency components. The next series here computes the inverse DFT by reconstructing the original series from its components. As mentioned last week, xn and ck are arrays of complex numbers, one in the time domain and another in the frequency domain. As we learned in algorithm design, the time complexity is a metric to describe the amount of computer time it takes to run an algorithm. We use this metric to evaluate the performance and efficiency of applications. This data structure here represents array C that stores the Fourier components of a given signal x, including n points. Forward DFT series sums up n terms to compute one frequency component. For instance, to compute C0, the DFT series should add n numbers. Computing one element in C takes O n time. There are n components like this in the array, so it means that the total complexity of computing n Fourier components in C is equal to O n square. Similarly, the IDFT series takes the same amount of time to reconstruct the original signal. Therefore, analyzing signals using the naive DFT series with such a high time complexity is not efficient enough and will be too slow in practice, especially when the input size is quite big. Today, we want to obtain an alternative approach to speed up the Fourier transform computation. For finding a faster algorithm, we first need to understand the nitty and gritty of the naive DFT series. Let's start with a small signal including 2 points. For this sample signal, the forward DFT series gives us C0 equal to x0 plus x1 and C1 component, which is presented here. We know that anything raised to the 0 power is equal to 1. That is why there is no term with an exponential function in the C0. Please note that we ignored the 1 divided by n normalization factor in the DFT series to avoid distraction. Let's again employ forward DFT series to compute Fourier components of a signal with 4 points, x0, x1, x2, and x3. Here, we can see the Fourier components of the input signal, which are C0, C1, etc. In this slide, we separate the terms into even and odd indexed subsequences. So as we can see, in each Fourier component, x0 is grouped with x2, while x1 and x3 are put together. There is also one more simplification that can be applied at this step. We know e raised to the minus 2i pi power is equal to 1. So, as presented here, the first term in C3 can be rewritten as e to the power of minus I pi. Okay, in the next step, let's replace our even and odd groups with C even and C odd as defined here. In our example, C0 even is equal to x0 plus x2, while C0 odd sums up odd terms which are x1 and x3. If we carefully look at the Fourier components rewritten using C even and C odd terms, we can find some common sub-expressions. For instance, we have C0 even and C0 odd in both C0 and C1. There are the same repetitions for C1 even and C1 odd. In the following slides, it is discussed how this great feature can be used to speed up the Fourier transform analysis. We are very close to obtaining an algorithm calculating the discrete Fourier transform faster. Let's compare C evens in the previous slide with the Fourier components for n equal to. With this comparison, we can conclude that C evens are the same as the DFT components of a signal that consist of 2 points x0 and x2. Similarly, C odd coefficients are Fourier components for a signal of 2 points x1 and x3 that are the odd indexed points of the input signal with 4 points. So, as explained in the previous slide, we can obtain the DFT of a signal with 4 sample points using two n equal to DFT calls. One DFT analyzes the 2 even index points of the input signal, and another one transforms the other 2 odd index points. In fact, the components of the two n equal to DFTs are combined in a way to obtain the Fourier components of a signal with 4 points x0, x1, x2 and x3. In the same manner, it can be proved that the DFT of a signal with n points can be reduced into 2 DFT with the same size of n divided by 2. In this slide, we want to formulate the components of a signal with n points based on the components for 2 signals with the size of n divided by 2. In this formula here, it is expected that n is even. Consider an input signal consisting of n points, x0, x1 to xn-1. So, in this equation, C even coefficients correspond to the DFT components of the signal consisting of even elements of the input signal x, including x0, x2, x4, etc. Similarly, C odd coefficients represent the DFT components of a signal consisting of odd elements of the input signal x, such as x1, x3, x5, etc. So, as we can see in this slide, a larger problem with the size of n is broken down into smaller problems with the size of half n. This technique, I mean solving a larger problem by dividing it into smaller subproblems, is called divide and conquer problem solving strategy. We learned this technique in algorithm design. The divide and conquer formulation discussed in the previous slides is the foundation for Cooley-Turkey fast Fourier transform. Cooley-Turkey FFT is an algorithm that determines the discrete Fourier transform of an input signal significantly faster than computing it directly. This recursive algorithm reduces the number of computations needed for a problem of size n from O n square to O n log n. You might ask why the time complexity of the FFT algorithm is O n log n. Suppose the time to compute the transform using this formula is a function like Tn. The computational operations such as additions, multiplications, and complex exponentials in the formula take O(n) time, and calculating the two half-n DFTs takes time 2Tn divided by 2. So Tn is equal to O(n) plus 2 multiply Tn over 2. Based on what we learned in algorithm design, the depth of recursion in this equation will be log base 2n. So the overall time complexity doesn't exceed n log n. In this slide, I want to present how faster can be FFT than the naive DFT. Have a look at the table we have here. The table compares naive DFT with FFT in terms of time complexity. Suppose it took 1 nanosecond to perform one operation. Then it would take the fast Fourier transform algorithm approximately 30 seconds to compute the discrete Forte transform for a problem size of n to the power of 9. In contrast, the regular algorithm would need several decades to do the same task. It is too long, isn't it? We can also apply further optimization to the recursive formula in slide 12 to enhance the FFT performance. Let's replace the exponential factor e to the power of minus 2i pi k over n, which is technically known as Tweedle factor, with its equivalent that is minus e to the power of minus 2i pi k minus n over 2 over n. We can see the modified formula here. In this formula, the Tweedle factor in the first case is equal to the Tweedle factor in the second case. For instance, the Tweedle factor in the first case for k equals 0 is equal to the Tweedle factor in the next case when k is n divided by 2. We can observe this equality for greater values of k. So, this replacement allows us to compute the Tweedle factors for k's less than half n and reuse them in the second case. This way, we can skip some complex exponential calculations and consequently enhance the FFT algorithm's performance. So far, we have discussed 1D fast Fourier transform. We can calculate the fast Fourier transform of a multidimensional signal by applying the 1D FFT to each dimension in the signal. For instance, here we have an m by n signal. We can obtain the FFT of the two-dimensional data just by performing a one-dimensional FFT on all rows of the data, followed by a one-dimensional FFT on all columns of the data resulting from the previous 1D FFT. 2D FFT reduces the number of computations needed for a problem of size m by n from O mn square to O mn log mn. It takes n log n to obtain the FFT of one row. The matrix consists of m rows, so obtaining the Fourier components of all rows takes mn log n time. In the same manner, calculating FFT of columns requires nm log m. So, the time complexity of 2D DFT is totally equal to mn log mn. In the following weeks, we will implement and use the fast Fourier transform in image processing and image filtering. With this, we come to the end of today's lecture. Thank you for your attention.